Hi folks. Up to this point, we've been thinking about elements being either metals or nonmetals. So either something that loses electrons or something that is greedily trying to obtain a few more, be that by stealing them from the metals or by sharing with each other. What we haven't done is really dive into the idea that it's a bit more of a spectrum. That is, that certainly metals over here don't tend to hold their electrons very strongly, and nonmetals hold them very strongly, but that in between you've got every flavor you could possibly ask for. And some nonmetal atoms pull really hard on the electrons in a covalent bond, and others not nearly so much. Now, the ranking system we employ is something called electronegativity, designed by Linus Pauling, a professor at UC Berkeley. It's a way of describing how intensely each atom is going to pull on the electrons in a bond. And when you have two atoms bound to each other that don't match up very well with each other, the result is that the electrons tend to spend more time with one of the two atoms, and as a result you end up with a polar bond, something with a positive charge on one side and a negative charge on the other. Let's take a look at that table. Here is Pauling's electronegativity chart. And what I want you to notice is that high numbers are going to correspond to atoms that pull very strongly on electrons, that tend to take on negative charge when they're in molecules. So, not terribly surprisingly, it's things like fluorine, oxygen, chlorine, things that are very close to looking like noble gases and are the most non-metallic of the non-metals. On the other hand, metals tend to have very, very low electronegativities, so they tend to be positive when they end up in bonds because they lose out on their electrons, either a little bit or altogether. Now, before we look at how this is used to rank the combatants on either side of a bond and determine whether one side becomes positive and the other side becomes negative, let's try and solve the problem from our last video about which of the cyanate structures was the best one. Take a good look at nitrogen and oxygen and ask yourself, before we move back to the worksheet, which one of those atoms tends to be negative more often. Now, we said in the last video that one way of thinking about oxygen and nitrogen not being quote-unquote happy in these two structures is that they are in fact the atom that has taken on the extra electron that makes this an anion. And so if we think about it that way, the question then becomes, which of these two atoms is more likely to suck up an extra electron? Which one will have a stronger pull to claim it for itself? And what I hope you come up with is that it would definitely be the oxygen, and that would make this the best structure of the three. Now, just as we did a quick comparison between nitrogen and oxygen to solve that problem, we're going to do the same thing anytime we see a covalent bond and look at the elements on either side of the bond. And what we'll look to do is compare the electronegativities and see if they are different enough to yield a polar covalent bond. So what we can do for each of these is just go down the line and determine the electronegativity of the atom on either side of each of these bonds that appeared in our Lewis structures. So for instance, carbon, wherever I see it, I can look at the chart that was on the earlier portions of the video and see that it's got an electronegativity of 2.5. So wherever I see carbon, I'll put in 2.5. Looking at hydrogen, that's 2.1. That's the only place it appears. Oxygen, a big fat 3.5. In fact, besides fluorine, oxygen is the queen of electronegativity. And we've got oxygen here, and here, and here as well, and also there. Phosphorus, very similar to hydrogen as a matter of fact, 2.1, shows up there and there. I missed a hydrogen earlier. There's a 2.1. Bromine, 2.8. It is a halogen, but it's a little bit bigger. The electrons are further from the nucleus, so it doesn't pull quite as hard. Chlorine, 3.0. We'll put that there and there. Fluorine, as we said, is in fact the queen of electronegativity, 4.0. And nitrogen, 3.0. And so what we can do now is look at the difference between the two in electronegativity, and I'm specifically going to put a little absolute value sign on that because we're really less interested in whether this number comes out positive or negative than we are how big it turns out to be. So as we go down the line, CH, a difference of 0.4, CO, a difference of 1.0, PBr, 0.7, ClCl, 0, OH, a difference of 1.4, OCl, 0.5, OF, 0.5. Phosphorus, phosphorus, 0. NO, 0.5. And NC, 0.5. So one thing we can see right away is that if I have the same atom on either side, I wind up with no difference in electronegativity. That is not going to be a polar bond no matter what we do. There is one bond on here, though, whose difference is so small that it doesn't tend to produce evidence of polarity in structures that it's part of, and that is the CH bond. In fact, it, for the most part, delineates for us the boundary between polar and nonpolar. What we're going to say is that delta ENs that are greater than or equal to 0.5 give you a polar bond. 0.4 and down do not. And so every other bond in this chart would be polar because we've got a difference in electronegativity of at least 0.5. Now, one way we're going to draw this is by showing the negative and positive poles of these bonds in drawings. And we generally use a small lowercase delta with delta minus and delta plus to indicate the presence of a partial positive or partial negative charge. And so if I look at the bonds that were polar, CO, PBr, OH, OCl, OF, NO, and NC, what I can do is look at these numbers up top and say to myself, whichever one of these atoms won the tug of war, that side is going to be more negative now. And so for carbon and oxygen, O wins the tug of war because oxygen is much more electronegative than carbon. So I'll have a delta minus here and a delta plus there. For phosphorus and bromine, same direction as it's going to work out here. Bromine, the more electronegative atom. For oxygen and hydrogen, oxygen's going to win. In fact, oxygen is going to win a lot. On the other hand, fluorine will take oxygen's lunch money because it has that electronegativity of 4. Anything else, though, bound to O is going to lose out. Lastly, N and C, nitrogen, the more electronegative of the two, and that's what we've got. There is one other very common way that we represent dipoles like this. That is, again, a positive pole and a negative pole, and that's with an arrow. And the arrows are going to come in very handy when we start looking at three-dimensional molecules in next week's work. The way a dipole arrow is drawn is that you draw it pointing towards the negative side, basically pointing towards the electrons. And what we do is we start with what looks like a plus on this side, and then draw the arrow pointing to the negative side. So you can almost convince yourself that you're seeing in the midst of this a positive and a negative. Okay? And so again here, PBr would also point to the left, towards the right rather, towards the bromine. OH is going to point towards the left, towards the oxygen. So is the ClO dipole. OF is going to point towards fluorine, to the right. And O is going to point towards oxygen, to the right. And NC is going to point towards nitrogen, to the left. So we have the arrows and we have the partial charges. Partial charges are a very good way to just indicate a part of the molecule that might have a negative charge. On the other hand, if you're going to have to start adding together dipoles, you want to look at the arrows. Now there is one very important limitation to electronegativity. You'll notice the only thing we've used it for so far is determining whether a bond is polar. But by itself, this cannot determine for me if a molecule is polar. The only exception to that is something like carbon monoxide, or for that matter, the diphosphorus molecule, because in those two cases, the molecule was simply a single bond. Maybe a double or a triple, but one bond. When I have multiple bonds that each have dipoles, in order to determine if the whole molecule has a positive side and a negative side, I need to know what its shape is. And that, I hope, whets your appetite for what we're going to be doing in the first half of Module 6. Before you rush off to that, though, you need to make sure this week's skills are nice and strong. So be sure to take care of your homework assignment. Make sure you post to the discussion board with your assigned Lewis structure, explaining in detail what it is you're doing. and then of course take the review quiz to see if it's all settling in really nicely. Stop by my student hours if you need any help, and I'll see you next week for Module 6. Take care.